Our topic for today is successive differentiation, and you are welcome to my YouTube channel. By successive differentiation, we mean if y is equal to f of x, the y dx is the first derivative. The second derivative will be f prime prime, and the nth derivative will be fn x, provided they all exist. Let's look at some worked example. In this case, you're asked to find the nth derivative of y when y is equal to 1 over x minus 2 raised to power 3. Now, let y be equal to x minus 2 raised to power minus 3. For f of x, it is equal to x minus a raised to power m, where m is minus 3 and a is equal to 2. Hence, we are going to have minus 1 raised to power n times 3 times 4 times 5 and continuing to n plus 2. Now, since 3 times 4 times 5 continuing to n plus 2 is equal to n plus 2 factorial all over 2 factorial, we obtain that dn dxn, which is the derivative on the nth term, will give us minus 1 raised to power n plus 2 factorial all over 2 times x minus 2 raised to power n plus 3. Let's look at another example. We should find the nth derivative of y when y is equal to sine x. Recall that y equal to sine x is a periodic function. Then its first derivative is y prime equal to cos x. And y prime equals to cos x, because it's a periodic function, you can change it back to sine and add pi over 2 to it. Now, when you continue in that thought process, you're going to discover that y prime prime will give us cos x plus 2 times pi over 2. And when you return it back to sine, you're going to have that y prime prime will be equivalent to sine x plus 3 times pi over 2. Now, following this argument, you're going to discover that the nth derivative of y will give us sine x plus n pi over 2. Now, following this thought process, we are going to look at this simple example. We should find the nth derivative of y when y is equal to sine 3x. The derivative of sine 3x are periodic, thus dny all over dxn will give us 3 raised to power n sine 3x plus n pi over 2. You can do the show working to confirm the result. Now, our next topic is the Leibniz theorem. The theorem states that if ux and vx are functions of x with derivatives up to order n, then the nth derivative of their product is given by dn over dxn of uv will give us the summation of nk and those derivatives there, where nk is equal to n factorial all over k factorial times n minus k factorial. Now, we can show the proof by using mathematical induction, which is what we have done here. You know the thought process for principles of mathematical induction. When you apply it religiously here and do the little differentiation side by side, you're going to confirm that the result holds for n plus 1 and hence for all n that is in the set of natural numbers. Let's look at some worked examples. Now, if y is equal to cos arcsine x, show that 1 minus x squared y prime prime minus x y prime minus y is equal to 0. Solution. Let y equal to cos arc sin x be written as shown on the screen, and let u be equal to arc sin x. You are going to have that y will be equal to cos u. And by the time you take the first derivative, you're going to have that y prime is equal to sin arc sin x all over square root of 1 minus x squared. And when you take the second derivative, you're going to have that y prime prime will be equal to cos arc sin x all over 1 minus x squared plus x sin arc sin x all over 1 minus x squared raised to power 3 over 2. Now, by the time you evaluate directly, you are going to see that 1 minus x squared y prime prime minus x y prime minus y will definitely give you 0 as stated in the question. Let's look at more examples. If y is equal to x minus square root of 1 plus x squared raised to power m, let's apply the Leibniz theorem to show that 1 plus x squared y raised to power n plus 2 plus 2n plus 1 xy raised to power n plus 1 plus n squared minus m squared y raised to power n is equal to 0. In this case, we are not going to do direct substitution. We are going to use the Leibniz theorem. Now, let our y be equal to x minus square root of 1 plus x squared raised to power n. And we make our u to be x minus square root of 1 plus x squared. Then our y will be equal to u raised to power m. Now, when you take the first derivative, you're going to have minus m over square root of 1 plus x squared y. And when you take the second derivative, differentiating again, you're going to have m squared plus xy prime square root of 1 plus x squared all over 1 plus x squared y. This leads to the second order differential equation. Now, applying Leibniz theorem for higher derivatives, we'll simply do a direct substitution into the Leibniz theorem, and we are going to have that 1 plus x squared y raised to power n plus 2 plus 2n plus 1 xy raised to power n plus 1 plus n squared minus m2 yn is actually equal to 0. Thank you for listening.